Hey, welcome to The Explainer. So today, we're diving into a really cool breakthrough in 3D printing, and it's all about precision. We're not just talking about what you build, but how you build it, right down to the actual shape of the light you're using.
So, let's kick things off with a pretty mind-bending question, one that's really at the core of a lot of modern manufacturing. I mean, it sounds like something straight out of sci-fi, right? But believe it or not, new research is making this a reality.
All right, first things first, let's get on the same page about the core technology we're talking about. It's called laser powder bed fusion, or LPBF for short. Now, you can basically think of it as 3D printing, but for metal. A super high-powered laser melts this fine metallic powder, and it builds up these incredibly strong parts, layer by tiny layer. We're talking parts for things like aerospace and even medicine.
So at the heart of this whole process is obviously the laser. And for the longest time, there's been pretty much one standard, go-to way of doing things.
Yeah, the default laser you'll find in pretty much every one of these machines is what's called a Gaussian beam. And honestly, the easiest way to picture it is to think of a tiny but incredibly powerful and super focused spotlight.
So the main thing to get about this kind of beam is just how concentrated the energy is. I mean, all the power is focused right there in the middle, creating this single super intense point. It's kind of like a sharp, hot needle of light that's drawing the metal part into existence.
Okay, but here's the catch. That intense focus, while, yeah, it's super powerful, it also creates some pretty big problems when it comes to the quality of the final part. What happens is that this massive concentration of energy creates an extreme hotspot. It melts a really deep, narrow pool in the metal powder, and that pool then cools down pretty slowly. And those specific conditions, well, they can actually mess with the internal structure of the metal, and that ultimately affects the strength of the whole part.
And this really gets to the heart of the issue. As this quote from the research points out, the very tool that makes this kind of printing possible is also the thing that's holding back the quality. It's a classic engineering paradox.
So, if this super focused point of light is the problem, what's the solution? Well, it's not about turning down the power. It's about changing the shape of the light itself.
And that solution is something called laser beam shaping. Basically, it's the whole process of changing the laser's intensity profile. So you're moving away from that sharp needle of light and you're turning it into something more like a paintbrush or a roller, or maybe even a custom spray nozzle. It all depends on what you're trying to build. All right, so let's take a little tour of some of these new laser shapes and see exactly how they help build a better part, literally from the ground up.
So the first alternative is actually pretty simple. You just take that standard Gaussian beam and you stretch it into an oval or an elliptical shape.
And right away, the effect is huge. Just by spreading that energy out a little bit, you can see the peak temperature drops a lot, and the width of the molten metal pool, it gets bigger by almost 30%. It's a really simple change, but man, what a big impact.
Okay, next up we have something called the top hat beam. Now, instead of having all that energy peaked in the center, this shape spreads the laser's power completely evenly across a circle. It's like painting a perfect flat disk of light onto the metal.
And this even distribution makes a massive difference. First off, it drops the peak temperature by over 600 Kelvin. That's huge. But what's really crucial here is that it lets the metal cool down faster. And that faster cooling, that's the secret sauce for creating a much stronger internal structure in the finished part. All right, now for something completely different. What if you took all that energy out of the center and you put it all into a ring instead?
Well, the effect on temperature is just, wow, it's dramatic. You can see on the chart, the ring shape makes that peak temperature just plummet. We're talking down to nearly half of what you get with the standard beam. Spreading the energy out like this gives you a much more gentle and controlled way to melt the metal.
So when you put it all together, this table really shows you the incredible new level of control we're talking about. Just by changing the beam shape, engineers can now literally pick and choose the exact melting conditions they need for the job. It's like having a full menu of options to build the absolute perfect part.
Okay, so what does all this mean? Having all these different paintbrushes of light, what does that actually mean for manufacturing? What's the big picture? Well, the really crucial point here is this. The goal isn't to just throw out the old Gaussian beam. Not at all. It's about building a brand new, super versatile toolbox. One where you can pick the perfect laser shape for a specific material or even a specific part of a single design. And honestly, this level of control is a total game changer. It lets engineers fine-tune everything, from temperature gradients to how fast the metal cools.
You're essentially designing the material's internal structure as it's being printed. And the result? You get stronger, more reliable parts with way fewer defects. And if we look to the future, this just blows the doors wide open for truly smart, adaptive manufacturing. We're talking about systems that can tailor a material's grain structure in real time, systems that use sensors to change the beam shape on the fly, and maybe most excitingly, it could unlock our ability to print with new, advanced alloys that were just impossible to work with before.
You see, this technology is moving us beyond just designing parts. We're getting to the point where we can design the very materials those parts are made of, almost atom by atom. And that leaves us with one last really exciting thought. With this kind of incredible control, what are we going to build next?